Hi everyone, my name is Shuo Wang, and I'm very happy to present our paper, a new information complexity measure for multipath streaming with applications. And this is based on the joint work with Mark Braverman, Sumega Garg, Chen Li, David Woodruff, and Jiapeng Zhang. And let me first introduce some background knowledge about streaming algorithms. A streaming algorithm usually takes a data stream. Here, we use x1, x2 to xn to denote the data stream as its input. And it uses bounded space to achieve its computational goal. Here, we use S to denote the size of the space. And it often reads and processes one data each time, and it will scan the whole data stream for one pass or multiple passes. And in this paper, we consider the space complexity S of the streaming algorithms. And the below picture is a demonstration of the one-pass streaming algorithms. And we use M1, M2, M3 to Mn to denote the memory states of the streaming algorithms. And we use X1, X2 to Xn to denote the input data stream. And we use R1, R2, R3 to Rn to denote the private randomness of the streaming algorithm. And as you can see in this picture, Mi is determined by Mi minus 1, Xi, and Ri together. And the first problem involved in our paper is called the coin problem. In the coin problem, one is given a data stream of length n, and in the data stream, each data is independently and uniformly sampled from 0 and 1. The question is, what is the space complexity to compute majority? And for this problem, we have a very trivial upper bound. We could maintain a counter of the summation of all the data, xi, and it will cost us O log n bits since the total sum of those data is at most n. And an interesting problem is that could we do better than that? And previously, Braverman, Garg, and Woodruff gave a partial answer to this question. They show that for any one-pass streaming algorithm, they require omega log n space to compute the majority. But could we extend their results to multi-pass streaming algorithms? And for the needle problem, is the second problem involved in our paper. The goal is to distinguish between data streams from two distributions. The first distribution is called the uniform distribution. In the uniform distribution, each data xi is uniformly sampled from a domain T. And in the needle distribution, we first uniformly sample needle x from T, then each data independently with probability p equals x, and otherwise is independently and uniformly sampled from T. And the intuition behind the difference of those two distributions is that when the domain is large, the uniform distribution have less collisions. And however, in the needle distribution, since we first sample a needle and then each data with probability p equals the needle, we have a lot of needle elements appeared in the data stream. And for the needle problem, we have a upper bound of O1 over p squared times n bits, and this exists for most of the parameters. And on the contrary, Lovett and Zhang proved a near optimal lower bound. They showed that for K-path streaming algorithms, it required omega 1 over kp squared times n log n space to compute the needle problem. And it is also widely conjectured that theta 1 over p squared n is a tight bound. Then let me introduce our main results of this paper. For the coin problem, we proved that for any k-path streaming algorithms, require omega log n over k bits to compute the majority. And this result extends the previous result for one-path streaming algorithms, and it also implies the tight bound for constant path streaming algorithms. Yeah, since when k is constant, we know that the space lower bound is also omega log n, matching the upper bound. And for the needle problem, we showed that for any k-path streaming algorithms, require omega 1 over kp square n bits. And we also improved the previous upper bound. We showed that there exists a one-path streaming algorithm using O1 over p square n bits, and this upper bound holds for a larger range of parameters. And together with our improved lower bound and upper bound, we showed that theta 1 over p squared times t is the tight bound for most of the parameters. And then let me introduce our proof used in our proof of the lower bound. Yes, here we first fix some notations. We use O to denote the one-path streaming algorithm, and we use OJ to denote the J's memory state of the one-path streaming algorithm, and which could be a random variables. Its randomness comes from the input data stream, since the input data stream could be a random variable. And it also comes from the private randomness of the streaming algorithm itself. And here we use XL to denote the else input to the one-path streaming algorithm. And XL could also be a random variable. And in the previous paper, Braverman, Garg, and Woodruff proposed a strong information complexity notion for one-path streaming algorithms, which is defined as follows. And intuitively, it is a summation over the mutual information between all pairs of OJ and XL, and plus condition on L minus 1. And there is a very good property of this one-path streaming algorithm information complexity notion, since it is upper bounded by n times s when x1, x2 to xn follows a product distribution. And since it has an upper bound, we could it suffices to show a lower bound for this notion in a specific problem, and then we could obtain a space complexity lower bound. And in our paper, we proposed a new information complexity notion for k-path streaming algorithms as an extension to their one-path streaming algorithms information complexity notion. Let me first fix some notations. Here we use M to denote a k-path streaming algorithm, and we use Mij to denote the J's memory state in the ith path of the streaming algorithm M, and also XL as the else data in the data stream. And our notion is defined as follows. Similar to the one-path notion, our notion intuitively, it is a summation over all pairs of Mij and XL plus condition on some of the transcripts. And there is also a very good property of this notion, since it is upper bounded by 2 times k times ns. Here, k denotes the number of passes, n denotes the length of the whole data stream, and s denotes the size of the memory. And this always holds when x1, x2, and xn follows a product distribution again. And then let me introduce some idea behind the proof. Maybe first for the coin problem. Since we have an upper bound for our information complexity notion, it suffices to show a lower bound omega n log n lower bound in the coin problem, then we could have our main theorem for the space complexity lower bound. And to prove the important lemma, we use variance information trade-off for k-path streaming algorithms. The informal version is as follows. For any constant epsilon bigger than 0, there exists constants delta and lambda bigger than 0, such that if the information complexity is smaller than delta n log n, and the entropy of mi, here mi denotes the end memory state of the ice path, and HMI is smaller than n to the lambda, then the expectation of the variance condition on the end memory state is relatively large. And intuitively, we could understand this main theorem as if the information complexity is small, the streaming algorithm could not precisely capture the whole data streams. And with the main theorem, we could prove our space complexity lower bound by first, we know that if a streaming algorithm, a multipath streaming algorithm has a high accuracy in the coin problem, and by the lemma proposed in BGW, we know that the variance is relatively low, and by the main theorem, we know that if the expectation variance is low, it would imply a lower bound for the multipath information complexity. And a lower bound for the multipath information complexity together with the upper bound of the multipath information complexity, they would imply a lower bound for the space complexity, omega log n over k lower bound. And the idea behind the proof for the main theorem is that is a reduction approach. Let M be a k-path streaming algorithm with high accuracy on the coin problem. We use M to construct a one-path streaming algorithm O such that the one-path information complexity of O is smaller than multipath information complexity of M plus C times n log n for small constant C. Here, intuitively, we know that we use M to construct an O, and we don't use much additional information to in O rather than M. And the second condition, the second thing is that the variance is relatively small. Condition on the end state of the one-path streaming algorithm, which also means the one-path streaming algorithm O also have a high accuracy on the coin problem. And by main theorem proposed in BGW, they showed that if the variance is relatively small, which means the one-path streaming algorithm O could also compute the majority, it would imply the one-path information complexity for O is bigger than omega n log n. And together with the first statement, we know that the multipath information complexity for M is also bigger than omega n log n. And then let us step into the proof for the needle problem. In the needle problem, we show that the multipath information complexity is bigger than omega 1 over p squared. And here, note that the multipath information complexity is built on the input data stream follows the uniform distribution. And let me first introduce some notations here. Here we use D0 to denote the uniform distribution. and D1 to denote the needle distribution. Maybe we should recall the definitions of those distributions. In the needle distribution, each data is uniformly sampled from T. And in the needle distribution, we first sample a needle, and each data with probability P equals a needle, and otherwise is uniformly sampled from the domain T. And another new defined distribution is called ds. Here, S is a parameter and it is a subset of N. And it is a hybrid distribution. And for those are not in S, xi are independently and uniformly sampled from T, just like the uniform distribution. And for those coordinates I lies in S, we first sample a needle X, and then each xi with probability 1/2 equals the needle, and otherwise is uniformly sampled from T. And intuitively, ds is a hybrid of the uniform distribution and the needle distribution with needle probability boosted to 1/2. In the coordinates lies in S, it performs like a needle distribution, and for those coordinates not in S, it performs like a uniform distribution. And the key idea in this proof is the decomposition of the needle distribution D1, and it is decomposed by a resample process. We first sample some potential needles at a set of S, and then sample data stream with DS. To be more specific, we could see in this below picture. First, we have a set of coordinates from 1, 2, 3 to n, and then each element in n with probability 2 times p to be contained in S. And now we have a set of potential needles S from P1, P2 to Pm. Then we sample a data stream with ds. And we could verify that the resample process is identical to the sample process of the needle distribution D1, since every element with probability 2 times P times 1/2 to equal the needle, and with probability 1 minus P to be sampled uniformly. And from the decomposition process, we could also rewrite D1 as a linear combination of ds. And from the decomposition process and from the linear combination of D1, we know that if a streaming algorithm could distinguish between D0 and D1 by an average argument, we know that the streaming algorithm could also distinguish between D0 and ds for a constant fraction of S. And for a fixed coordinate set S equals P1, P2 to Pm, we know that if a streaming algorithm could distinguish between D0 and ds, the information complexity ICS is bigger than omega 1. Here, ICS is defined by the following statement, and intuitively, ICS is the mutual information of those transcripts whose positions is near to the S between the data input of those positions lies in S. And the intuition about this statement is that if since the differences between D0 and ds only lies in the coordinate set S, this is because in the coordinates not in S, D0 and ds both follow the uniform distribution. But in in S, ds is like a needle distribution. And if a streaming algorithm want to distinguish between those distributions, the memory state of the streaming algorithm must contain a lot of information of those data input lies in the coordinates S. And this is the technical part in the proof of the needle problem, and it is a bit complicated. So I would like to refer you for the proof to our paper. And from the two statements above, from the two facts above, we know that if we take expectation over S and take expectation of ICS over S, it will equal the summation over S, the probability that S is sampled by the process, times ICS. And we know that if the streaming algorithm could distinguish between D0 and D1, they could distinguish between for constant fraction of S and for those S such that the streaming algorithm could distinguish between D0 and DS, the information complexity ICS is bigger than omega 1. We know that this term is bigger than omega 1. And then we know that for information complexity, for mutual information term between Mij and XL appears in the ICS only if J plus 1 and L both lies in S. This is because the definition of ICS, right? And we know that J plus 1 and L independently with probability 2 times P to be contained in S. Thus, we know that the probability over S, J plus 1 L lies in S, is approximately P squared. And then we know that the multi-pass information complexity is bigger than omega 1 over P squared times the expectation, and which is also omega 1. And we know that the multi-pass information complexity is bigger than omega 1 over P squared. And this shows our main theorem for the needle problem. And at the end, I want to show that our two results for the coin problem and for the needle problem have a lot of applications in the streaming algorithm. The two results implies a lot of lower bounds for other streaming problems, such as the case frequency moment estimation problem in the random order, and the multi-L estimation problem, and the counter in strict turnstile streams. And there is also some other applications omitted here, and they are included in our paper. And at the end, I want to make a conclusion. I think in our paper, the very important contribution is that we proposed a new information complexity notion for the multi-pass streaming algorithms. And it is the first time we use information theoretical approach to directly prove lower bounds for streaming algorithms. Because previously, most proof for the multi-pass streaming algorithms lower bounds are from the reductions to some communication problem, and we use some lower bound for communication problem to prove the lower bound for multi-pass streaming algorithms. And I think our notion works for for most of the streaming algorithm problems as well as the notion is built on the uniform distributions. And then it will have a very nice upper bound. And a very interesting problem is that could we use this notion to prove some other streaming lower bounds, multi-pass streaming lower bounds for some other streaming problems? And yeah, that's all I want to share today. And thanks for all your listening. Thank you.